Hello, good morning. We are talking about acids and bases this unit. This will be our final unit of the year. Kind of a quick unit. We're only going to have about 5 days of instructional time before we have to start preparing for senior finals and then everyone else's finals. So we're going to get started. So acids are going to be everywhere. You're going to find acids in every single food that you eat. If you look on any nutritional label, you'll find some sort of acid. Acids and bases are what make our foods and drinks have different flavors. They also have lots of other different uses. So, how do you know if something is an acid or a base? So, the properties of an acid, they're going to be sour in taste if you were to taste it. And the other big one is that they're going to have a pH lower than 7. So if you have a pH between 0 and 7, it's considered an acid. Acids also conduct electricity very well. And then they also change your acid-base indicators. Some will react with metals, and we will talk about that more when we talk about reactivity. And then some of these will react with bases to produce salts and water, and we will talk about all that in a second. So these are just some examples here. This is an acid dissolving a sponge, and then this is an example of a titration. So if you see this little tube here, it's a glass tube. It's actually very tall, about 2 feet long, and you very slowly drop your other liquid in, and you're trying to get it to be neutral. So this has an acid-base indicator in it, and at the moment it becomes neutral, that changes color so that you can see that you have finished your titration, you've diluted it. So acid-base indicators, go back here. If you're interested, there is a video here about flesh-eating acid. We did watch it in class, but just for the sake of time, I'm going to skip it on this video. It's kind of yucky, but if you are interested in that, like the first 6 minutes or so, it's pretty good. So if you want to watch that, you can. So with the acid-base indicators, these are just different substances that are going to change color depending on certain pHs. So you have like pH strips. This is called a universal indicator. So you guys have probably used these at some point if you have a pool at your house or maybe in another lab. But you dip these into your substance. These little pads on here are going to change color, and then you match it to the colors on the key. So this is going to be a little more useful in as far as giving you a precise pH or a fairly precise pH. You're also going to have litmus paper. Okay, so that's what this video is showing. There's blue litmus paper and red litmus paper, and they're going to change depending on the acidity or alkalinity. So blue litmus paper turns red in presence of an acid, and red litmus paper turns blue in presence of a base. So that is something you need to remember. I know it's just going to take repetition, just practicing it. So if the red turns blue, it's a base. So you have blue base. If it turns red, it's an acid. So someone the other day said, well, you can remember this because if you're angry, you're going to turn red, and acids are angry, I guess. So that's one way to remember it. So you have angry acids, they're turning red, and then blues are basic. So that's the change of color. Okay, so this here shows you've got your blue litmus paper, it's turning red because this is an acid. And then this red litmus paper just doesn't change color, it stays red because it's an acid. So there's lots of different uses for acids in industry. Sulfuric acid, widely used in manufacturing, especially like metals and things like that. It's really, really good at pulling out the carbons or separating the hydrogens, I should say, from the carbon and oxygen. So that's what this video is showing. This is just sugar in a beaker with sulfuric acid. So that sulfuric acid pulled all of those hydrogens and oxygens out and just left the carbon behind, which is this big black piece here. Some more uses, nitric acid. This is usually used in making explosives and things like that. You can see it's kind of this bright orange color, so it would stain your skin if you got that on you for some reason. Phosphoric acid, really, really common. So this is going to be in any plant food, fertilizer, things like that. They spray it on fields. It's also a main component in most sodas. So if you look on a nutritional label for a soda, you're probably going to find phosphoric acid. The last couple here, you have hydrochloric acid. We know that this is found in our stomach to aid with digestion. It's also used to clean things like muriatic acid. You might have seen for swimming pools. You can use it to get substances off of buildings and things like that. Acetic acid, we've used this a handful of times in class this year. I'm sure you've used this at home. It's just vinegar. So diluted acetic acid is vinegar. It can also be used to produce plastics and things like that. So on to bases. Bases also change the color of acid-base indicators. They produce salts and water with acids, and they do conduct a little electricity. But the main thing with the bases is that they have a pH higher than 7. So the pH scale goes up to 14. So if your pH is between 7 and 14, it's going to be basic. And they're going to have a bitter taste, and they're going to feel slippery. So that's why soap feels slippery, because soap is a base. Okay, so that's kind of what this is discussing here. So they will taste bitter, and most people don't think about bases as being caustic or corrosive, but they are. So if you have a strong base, it can be just as harmful as a strong acid. So this here, we talked about this a little bit, and someone brought it to my attention that this might have been debunked by now, but I'm sure you've heard of these things before, at least, that we do have areas of our mouth that we're going to taste sour and bitter. But my main thing is that your sour taste comes from acids, and then your bitter taste is going to come from bases. Okay, so this is just kind of a quick review of those different indicators. So you have your universal indicator, red and blue litmus paper, and you can kind of see how you get a more exact pH measurement with the universal paper. So the meat and potatoes of this lesson is going to be your theories of acids and bases. There's going to be 3 theories that we're going to go over. So these are basically ways you can identify what will happen during a chemical reaction, like what the products will be. You can also see like how that is happening. So are they exchanging protons? Are they changing electrons? Things like that. So the first one is Arrhenius acids and bases. So Arrhenius acids, if you put one of these in water, it's going to produce a bunch of hydrogen ions. Okay, so hydrogen is going to be your positive ion when it's mixed with water. Since you have all these extra hydrogens floating around and you're already in water, most of the time it's going to produce hydronium ions. So not 100% of the time, but a lot of times. So if you see this H3O hydronium as a product, you are most likely looking at an Arrhenius acid reaction. So strong acids, we know that the hydrogens are going to kind of come out of that, but with strong acids, all these hydrogens are going to be dissociated completely. They are not going to go back into their original solution. But weak acids can reverse the reaction. That's where you get this forward and backward yield sign. So if you see this sign, the symbol, it just means that you have something that's a reversible reaction, and it is probably in equilibrium, equally producing and going back to its reactants back and forth. So most acids are going to be considered weaker acids, and they're going to kind of very easily kind of switch back and forth. One thing you want to look at here, if you notice something in common with all of these formulas, is that they all start with H. So acids will start with H in the front, and we know that it has to do with those hydrogens. So since hydrogen is your positive ion and hydrogen would dissociate from the rest of this molecule in water, we know that the hydrogen has to be here to start out with. So that's one thing to help you identify if it's an acid or a base. With the Arrhenius bases, just like with the acids, they're going to produce something. So the bases produce hydroxide. Hydroxide is a negative ion, and this is just in water, right? So if I take sodium hydroxide and I put it in water, that will dissociate into the sodium and then the hydroxide. So it'll kind of space out. So you have these 2 examples here. So we have hydrochloric acid plus water. We're going to yield the hydrogen ions plus the other component, which is the chlorine. And then for the bases, you have sodium hydroxide, and it's going to dissociate into its pieces as well. Arrhenius bases also have something to identify them by, so they're going to have these OH at the end. So this is hydroxide. So your bases are going to have hydroxide after them. All right, so an example, is this an acid or a base? This is a base because you can see that it has a hydroxide in it. What will be the only positive ion in this solution? Well, it starts with an H, so we know that it's an acid. Since it's an Arrhenius acid, it's going to be giving off hydrogen ions, which we know are also probably going to form hydronium ions. The next theory, we have 3 again. The next theory is going to be Bronsted-Lowry. This has more to do with how these acids and bases are acting in the reaction. So what's kind of the key to this one is that you don't actually have to have two acids or an acid and a base for these. You can have something that's neutral, like water, and it can act as an acid or a base, depending on how your hydrogens are going to be moved around as the product. So with your Bronsted-Lowry acids, your acids are going to donate their hydrogens during the reaction. So the reactant will have some sort of hydrogen, and the product of that same component is going to lose one of its hydrogens. For the bases, they're going to accept hydrogens. So what I mean by that is this. So we have water, and then we have ammonium. So if you look here, we have two H's on this water. You go over to the product side, you can see that this is the counterpart, the OH, because this has an N in it, right? So these two kind of match up, and we know that these two match up. So between the reactant and the product, we lost a hydrogen, okay? So since this water is donating its hydrogen, this is considered an acid in this reaction. So you would label this as your acid. Since your ammonia is gaining a hydrogen, this is going to be considered a base. So that's what you're going to be doing with these. You're identifying the pieces. So is it losing or gaining a hydrogen in the process? If it loses one, it's an acid. If it gains one, it's a base. All right, so if you're going to look at this one, which species is an acid and which is a base? So if we're looking here, we have water. We know that its counterpart is this hydronium. So in this process, it is gaining a hydrogen, which means it's going to be a base. And then this one, this hydrofluoric acid, it is losing a hydrogen, which means it's going to be the acid. So what that means, being that something can act as an acid or a base, is called amphoteric. So water is pretty much the only one you'll see. Sometimes you'll see that with other substances, but mostly just water. So if you see water in a part of a reaction, just be aware that it could be the acid or the base, depending on how these hydrogens will be exchanged. Then we have our conjugate acid-base pairs. So this goes right along with identifying the acid and the base again. So like I said before, you always have this counterpart on the product side. So we know that the water is going to have a counterpart of this hydroxide because they're made of the same materials, right? We have oxygen and hydrogen. So if we've identified this as the acid for this reaction, its counterpart will be the conjugate base. Okay, so every acid-base pair will be an acid and a conjugate base, or a base and a conjugate acid. So for this one, your NH3 we identified as the base. Its counterpart will be the conjugate acid. All right, so then you would identify these as your conjugate acid-base pairs, right? So this is all together on one page. This is probably a good reference for working through these. I always start with the reactant side and look at those hydrogens and identify which is the base and which is the acid. Then move to your product side and then identify what those are. So if you are losing a hydrogen on the reactant side, that's the acid, and its counterpart is going to be the conjugate base. Okay, so for this one, if we're trying to write out a conjugate acid-base pair, you first have to identify what the acid and base is, what the conjugate acid and bases are, and then you write them out, okay? You always want to write the acids first, and with just a dash between them. So in this one, we identified the hydrofluoric acid as acid. The conjugate base is going to be the fluorine, so it's going to be HF-F negative because we know that it's an ion now. Same thing over here. We identified this product as the acid, the conjugate acid, and then its base was the water. So even though this is on the product side, you're still going to write it first. So it's going to be H3O plus dash H2O. All right, so again, identifying the conjugate acid-base pairs, you're going to have you're just going to have to figure those out first and figure out which is the acid, which is the base. So with this one, this HCO3, we know its counterpart is here, so we're comparing the hydrogens. So this one's gaining a hydrogen in the process, so that means it's the base. This one's losing a hydrogen in the process, that means it's the acid. So this would be the acid, and this is its conjugate base, and that's how this is identified here. And then this one is our conjugate acid, and this one is our base, so that's how we've identified those. The last kind is Lewis acids and bases. We won't use this a whole lot, but I do want you to know what it is. This is used more commonly in organic chemistry. So if you plan on taking organic chemistry in college, this might be useful information. So Lewis acids and bases, the theory behind this is that they're going to accept or donate electrons, pairs of electrons. So hopefully this is a flashback to Lewis diagrams for you, Lewis dot diagrams. But if you're looking at an equation, you're trying to figure out which theory would define this acid-base reaction, a Lewis reaction is always going to have one product. So it's like a synthesis reaction. You're going to have a base and an acid. They're going to come together to form one product in the end. So that's how you can identify those. And this is a quick summary of those acids and base theories. So the Arrhenius theory, the Arrhenius acids and bases, these are going to, in water, either produce hydrogen or hydroxide. If you mix an Arrhenius acid with a base, you will produce water and a salt. So if you think about salts, it's probably back to periodic table, like unit 3. If you have anything in group 1 on the periodic table and group 17, mixing those together creates salt. So it doesn't have to be like sodium chloride. That's not what I'm talking about. But if you're mixing anything in those two categories, those two groups, it'll be a salt. So when you have an Arrhenius acid-base reaction, your product will be water and salt. The Bronsted-Lowry definition, this theory is going to be all just talking about how the hydrogens are moving around. This you're going to see a lot. This is going to be used often to identify these. So we know that the acids are going to be losing or donating their protons, which are their hydrogens, and then the bases are going to be accepting those protons, which are the hydrogens. Lewis, again, they're exchanging electron pairs. So you guys do have a practice on this. Please try to get through that and see how that goes for you. If you do have any questions, let me know. There is also a Quizlet that is designed just for this section of this unit. So if you go to Quizlet and you just search my username, it's Mrs. Sarah Bland, all like one word, no spaces. You can pull up like all of the sets. So if you want to join my class on Quizlet, you are free to do that. Then you have access to all of my practice sets here. So give that a shot, run through the Quizlet, and let me know if you do have any questions. Have a great day.